Welcome to this explainer. Okay, today we're taking a truly fascinating journey. We're going to dive right into the intricate, microscopic world of ARM microcontrollers. And then, well, we're going to zoom all the way out. We'll see how tiny, low-level code optimizations literally power the massive, macro-level Internet of Things. It's a journey from bare metal to global networks, and I'm absolutely thrilled to guide you through the whole shebang. So let's just dive right into this. Experts confidently predicted that by the year 2020, there would be 50 billion connected devices active across the globe. 50 billion! That is a massive number. But here's the catch, right? For all those incredibly diverse devices to actually talk to each other, stream data, and run seamlessly, the microscopic brains inside them, the microcontrollers, they've got to be hyper-optimized. I mean, every single clock cycle matters when you're multiplying it by 50 billion.
All right, here's our roadmap for today. First, we'll look at moving data on bare metal. Second, optimizing C for ARM. Third, handling exceptions and interrupts. Fourth, managing memory with stacks. And finally, entering the IoT ecosystem. Let's get right to it.
Section 1. Moving data on bare metal.
So we're starting our journey at the absolute atomic level of our processor hardware. We really need to look at how data is physically moved around inside the chip before any actual computation can even begin. At this level, there's this absolutely foundational rule. ARM processors use what's called a RISC load-store architecture. What does that actually mean? Well, in plain terms, you can't just do math directly on numbers sitting out there in main memory. No way. You absolutely must move your data from memory into the processor's 32-bit registers first using a load instruction, like LDR. Once it's there, then you can do your math. And finally, you use a store instruction, like STR, to put the result back into memory. It's a strict rule, sure, but honestly, it's exactly what makes the processor so incredibly fast.
Moving on to Section 2, Optimizing C for ARM. Okay, let's zoom out a bit to the software layer. You know, we rarely write in raw assembly code anymore. We use high-level languages like C. So let's see how the compiler actually translates our human-readable code into those strict bare metal instructions. And I've got a great puzzle for you here. You might intuitively think that using a smaller data type, like an 8-bit char, saves space and speeds things up compared to a bulky 32-bit int, right? Especially if you only need to count a small number, say from 0 to 64. But is that actually true on an ARM processor?
Well, surprise! The crucial point here is that using a char for a local variable actually wastes processor cycles. I know, it sounds backward. But because all ARM registers are inherently 32-bit, whenever you tell the compiler to increment an 8-bit char, the compiler has to manually ensure that if the number hits 255, it successfully wraps back around to 0. To simulate this 8-bit limit inside a 32-bit space, the compiler literally has to inject extra masking instructions, like an AND operation with 0FF, right into your code. If you just use a native 32-bit int for your local variables, you avoid these extra execution steps entirely. It's a real game changer for saving precious time.
Now check out the difference in how we can construct loops. On side A, we've got your standard textbook C loop. You start at 0, you count up to 64, and you check the condition every single time. But on side B, we have an ARM-optimized loop. We're using pointer increments to move through the data array, but more importantly, we're using a do-while loop that counts down to 0. So you might be wondering, why on earth does counting backward make our code faster?
Here's the secret. Counting down to 0 actively saves processor cycles. In a traditional loop, the processor has to add 1 to the counter, then use a completely separate compare instruction to see if you've hit 64, and then branch. That's a lot of steps. But when you count down, the subtraction instruction inherently sets the processor's condition flags automatically. The comparison with 0 is virtually free. By just counting down, the loop overhead drops to just 2 instructions, safely eliminating the need for a separate compare operation altogether.
All right, Section 3, Handling Exceptions and Interrupts.
Even perfectly optimized code needs a bit of a traffic cop when hardware emergencies strike. Looking at the processor's emergency dispatch priorities, we can see exactly how the chip manages crises. A system reset? That's priority 1. It trumps everything. But notice the difference between an FIQ, a fast interrupt request, and an IRQ, a standard interrupt request. An FIQ is priority 3, while an IRQ is priority 4. When an FIQ happens, it actually disables other interrupts entirely to ensure it gets handled with absolute minimum latency. The processor uses this strict hierarchy to make absolutely sure a minor software glitch doesn't block a critical hardware emergency.
So whenever one of these interrupts strikes, the hardware kicks off this automated step-by-step response. It instantly changes the processor mode, backs up the current program status register, saves exactly where it left off in the code to the link register, disables any further interruptions, and then branches off to a vector table address to run the software handler. Phew, that's a lot, but this sequence securely pauses your perfectly optimized loop, handles the hardware crisis, and then drops you right back where you started without missing a single beat.
Moving right along to Section 4, Managing Memory with Stacks.
Now, to safely pause during those sudden hardware interrupts without losing its place, the processor relies heavily on memory management tools. Let's talk about stacks. Think of a stack exactly like, well, actually it's pretty much just like a stack of plates in a cafeteria. When an interrupt happens, the processor pushes the current state of its registers onto the stack. It does this rapidly using a store multiple instruction, or STM. When the interrupt is done, it just pops them back off using a load multiple instruction, or LDM. Now, while ARM hardware supports stacks that grow up or down, the official ARM standard dictates we use full descending stacks. This just means the stack pointer always points to the last full item and it grows downwards in memory toward address 0.
And here is a remarkably clever design trick. Think about this. If your stack keeps growing downward and never stops, causing a stack overflow, it's going to eventually overwrite whatever is below it. If you put your stack at the bottom of memory, it'll crash right into your code and your crucial vector table. That's a total disaster. So, a clever embedded design places the interrupt stack high up at the very top of the memory layout. This ensures that if a runaway stack overflow occurs, it just descends into empty free space. This gives your system a fighting chance to throw an error instead of just immediately bricking the device.
And finally, Section 5, Entering the IoT Ecosystem.
Okay, let's zoom all the way out to the macro level. What are these hyper-optimized, perfectly managed microcontrollers actually powering out there in the real world? To cut through all the industry buzzwords, we really have to look at how the true Internet of Things differs from other concepts. People often confuse IoT with M2M, older direct point-to-point machine communication, like a telecom switch talking to another switch. Or they confuse it with Industry 4.0, which strictly focuses on the manufacturing floor. But the true IoT is a much vaster ecosystem. We're talking about billions of independent, web-connected endpoints, dynamically gathering and exchanging data via the global internet.
And the ultimate objective of this massive ecosystem isn't just basic connectivity for the sake of it. When we look at the intelligence flow, we start with those tiny endpoints and sensors generating massive amounts of raw, chaotic data. That data travels up through the network layer, gets filtered by information processing, and is finally viewed on analytical dashboards. The whole goal here is to transform raw physical sensor readings into structured, actionable knowledge. That's what drives smarter operations, whether you're looking at a smart city grid or an automated farm.
As the saying goes, information itself doesn't actually have importance until the point when it's unified and prepared into valuable data. And honestly, this is the vital takeaway of our whole explainer. The only way we can reliably gather, unify, and transmit that data in real time across billions of endpoints is because of the tiny, perfectly optimized hardware processes at the micro level. It's the efficient C code, the rapid hardware interrupt handling, and the smart stack memory layouts that make this entire world-changing data synthesis possible at the macro level.
It really leaves you wondering, doesn't it? If changing a single char to an int, or simply counting down a loop instead of counting up, can save millions of cumulative processor cycles across a vast network, well, what incredible impact will your low-level code have on our interconnected future? Every single cycle counts when you're building the foundation of the world. Thanks for joining me on this explainer, and keep optimizing.